All right, starting off day number 2, our opening keynote address is from Dr. Mark Weir. He's professor of environmental health sciences at the College of Public Health at The Ohio State University. He's developed his expertise in quantitative microbial risk assessment. We heard a little bit about this yesterday from some of our other speakers. His expertise is in water QMRA. His dissertation was seminal to the second generation of microbial dose response models. Dr. Weir is keenly interested in developing predictive analytics capabilities for QMRA modeling via predictive microbiology and smart modeling algorithms, which sounds like magic to me. He received his PhD at Drexel, and he was formerly at Temple before his defection to The Ohio State University. Dr. Weir?
Well, I'm going to go through, and the title might have changed a little bit. I'm kind of notorious for just slightly tweaking titles as I move along with the presentation. In the intro material, Jesse was mentioning I work now at The Ohio State, which, yes, you have to put "the" in The Ohio State. But I'm also working with Jesse building out his risk modeling capabilities here at NSF International in a tandem effort with Ohio State as well. And what we're going to be going through realistically this morning is not too intensive on all things QMRA because it's 8 o'clock in the morning and not even I really want to hear myself talk about QMRA, even though I've been doing it for 10 or 12 years. And the other thing is we're going to be making an interesting path through a number of different fields. So we're going to be trying to touch on public health, engineering, data analytics kind of methods, and then moving our way to where we can be at on an interior space contamination kind of situation. And so in light of that, I decided to wear a shirt with cufflinks, a blazer that doesn't match it, and then Merrill walking shoes to be functionally chic. So a lot of what we do right and wrong really comes around to the data. It's how we collect the data, whether that's going to be able to work within a model itself, and then being able to use data in a smart way. And so when I say smart systems models, what I'm basically saying is we don't always use data in the most intelligent way possible. Where we come from to be able to figure out what smart systems models are is first we need to understand what a system is, and then we need to understand how a system works and what kind of data needs to go into it. So a system, when we're talking about it from either in any kind of sense, really. So what we have when we're talking about a system is we have an ordered set of processes. So we could think of it from a system of being able to get coffee, where we have to go through the process of coming through the front doors, and thankfully nobody's overbearing in the front atrium area, which is very nice. And then you have to get through that corridor to be able to get over to the coffee, and then by the time you get to the coffee, you've completed the system of getting coffee. It's a very simple way of trying to describe it, but that's what we're talking about, is an ordered set of processes. In order to be able to model such a system, or being able to model a more complex system, we need the appropriate data to be able to move that model forward. So what we need to do is we need to understand not only what the data needs to go into the model, but then also be able to understand how to use that data in a more intelligent way. But first, what I wanted to do was kind of lead you through the path of QMRA in a general sense, and then where we're going to be able to use QMRA. So QMRA is quantitative microbial risk assessment, and that is as descriptive as it sounds when you first say it. But first, we want to give a little bit of a historical perspective from where risk really comes from. The actual beginning area where you had some kind of analytics associated with risk started in the Middle Ages, and it was all about the sea trades. How much am I going to lose if I lose this ship? Is this ship worth sending if I'm going to lose it? How much do I have to put on this ship in order to make it worthwhile to run the expedition? And if I lose it, I still don't lose that much money in the process. I like to think that risk is one of those original computational or pseudo-computational sciences or thought processes. And I take this all the way back to caveman days. So you have one person who has decided that it's a good idea to go after some kind of big dangerous animal. So you have somebody that goes, hey, see that big thing over there? That really big hairy thing with big horns coming off of it? It's mammoth. I'm going to call it a mammoth. I think we should go over there and hunt it and kill it. Look how much meat's on it. So the other person's over here, and usually if you're centered, it works a bit better. The other person's going, you're insane. Look at the size of that thing. It's going to crush us. There's no way we can survive getting it. Yeah, but then we have enough meat for the winter. Well, at least I'll have enough meat for the winter. So they kind of go back and forth, and then somebody decides that, yeah, it's a good idea to hunt this big, massive thing that's going to kill us, but they went through a risk assessment. They didn't do it on computation. They didn't do it on paper. They didn't have a calculator, obviously. But what they did was they assessed what the risk was, and then they decided on an action after they looked at what that risk was. We can do the same thing when we put on our seatbelts every time we get in the car, which hopefully everyone does. We can do the same thing when we have one last drink, or in my case, I smoked for 20 years, so at some point I did a risk assessment and said, I'm already 18 years into this thing, I might as well just kind of continue it. But from a computational sense, what we're really talking about is there's some adverse outcome and some consequence associated with that, and we want to be able to compute what that possibly could be. When we bring this into the health area, we need to first understand where our original basis is. We started with radiological, then chemical, and then from chemical we adapted out for microbial risk assessment, and it all came from the National Research Councils originally, giving out guidelines on how to use risk assessment in the federal government decision-making process. And that's really where we started getting a better idea of structuring what a risk assessment should be from a health standpoint overall. I really would recommend, if anybody wants to read a bit more about this Meynell and Ma paper is really very interesting as a root of where computational risk assessment starts to come from in a greater sense. So the real value of a risk assessment on a health aspect is we have a number of different possible consequences when we're talking about health. So if you go back to the idea of risicum back in the Middle Ages, they were really just worried about how much money they were going to lose. If we talk about it from a health standpoint, we can worry about infection, or we can worry about illness, or we can worry about mortality, or we can worry about the cost associated with that, or we could worry about whether we're criminally liable, negligently liable, and so on from there. So there's a lot of different ways of trying to view what a health risk outcome could be, depending on your personal position, as well as your responsibilities within whatever organization it is. But there's a number of different basic ideas that we can go through when we're talking about a health risk assessment. And really what we do a lot in my lab is trying to look at this remediation option. Is remediation even worth it based on what the health risks are? And so this kind of goes to the point of natural attenuation for chemical contaminants or other items like that. And if we're talking about my old roots in biodefense and bioterror arenas, how do we try and prevent something so that we don't have to worry about cleanup? And then if something happens, what kind of cleanup level do we have to actually go to? There we go. So microbial risk assessment, I put it back to about 1982 when Chuck Hawes first published the first mechanistic dose-response model for microbial hazards. Before that, we had used threshold models or chemical dose-response models or empirical models to be able to assess what dose of pathogens will result in what probability of response, be that infectious, illness, disease, or mortality. And in reality, we wouldn't be able to have the Q quantitative in QMRA if it wasn't for the dose-response model. That's really where we get the yardstick of risk. What's the actual risk that we would incur if we didn't affect this dose from getting into the host? And one of those issues what we're going to see in the future path is that individual host item. So the way I define QMRA is it has evolved from a useful computational tool that can be used in a number of different areas to a science in and of its own. It's a coupling of multiple different sciences, and the reason that it has to be considered a coupled science is that if you take apart this diagram, you're going to start falling apart. If you remove the microbiology, you're no longer going to be able to understand what the pathogen is, and therefore the M in QMRA falls apart. The mathematics needs to be in there so that you can actually make a model fit whatever models you need to, and then use them for whatever purposes you need to. Public health basically puts reality into these two guys. So the engineers and the mathematicians are really good at putting together the models and the statistics. The engineers are really good at understanding the physical world and how we're affecting it and how it's affecting us and what we can do by way of controls for it. And neither of them typically have an overtly good grasp of the constraints of public health analyses, that you need an appropriate power before you sample. so that your sample is actually representative of a population. And these kind of fairly basic concepts that we have in public health that engineers, mathematicians don't always get. I'm beating up on engineers, but I am an engineer. I'm just a somewhat reformed engineer overall. But what we can see is that QMRA is this cross-cutting field, and it is becoming itself, in and of itself, an independent science that we can drive forward. There we go. And how do we drive that forward? So we haven't been able to talk about a ton of what goes into QMRA because it's a broad field. It has a lot of different implications, and depending on where you decide to house those discussions in the water sector, the healthcare sector, the food sector, it's going to change slightly based on the data needs and what we can do by way of discussion on it. But we can see a bit of a path as we move forward. So we had the development of the field with the first dose response, mechanistic, physiologically plausible dose response model. That's an important concept. Mechanistic and physiologically plausible. That's what makes it more accurate than an empirical model or other options. So we have the actual genesis of the field itself, a massive explosion of it under the Center for Advancing Microbial Risk Assessment that was housed at Michigan State University. And that really caused an explosion of QMRA, and that's where we started realizing that this can and probably is its own independent world. Then what we ended up realizing was we needed to have advanced dose response models. We needed to understand how the human host or other host species physiology is affecting what's happening to that dose, and then what the resulting risks are based on those changes to it. And then as we moved forward, we started realizing we had a number of other issues. One is on the data that we're using in the exposure. We have a lot of values under a detection limit or over a detection limit, and usually there's this magic hand waving that goes, environmental data is messy. It's just, that's what it is. That's not good enough when we're talking about it from a health risk assessment standpoint. We need to be smarter with how we use the data. Instead of saying everything's zero just because I didn't see it, you need to take into account your detection limits. So the next set of analyses and models that need to come out need to start talking about that. We need to be able to incorporate socio-behavioral sciences and other behavioral sciences into QMRA directly. Right now, I will make out a QMRA model. When I get to the risk management point, I'm going to say to a social scientist or somebody else, well, how do you think behavior of the exposed population is going to affect their overall risk? And that's too late at that point. What their behavior is affects the exposure. It affects the dose response, even in some cases, depending on what the pathogen is. An increased stress level is going to either increase or decrease your overall risk that can be modeled out. So we really need to understand those behavioral sciences a lot better in QMRA. And this is where I beat up on engineers again. We're kind of the fault. We were the ones who were doing a lot of the modeling initially, and I don't talk very well to people at all, so I don't really want to do behavioral sciences that much. Then the next stages that we're going to get to are understanding persistence. We can't just say, oh, we're going to lose one cell every hour. That's not very helpful at all. What is it dependent on temperature, pH, surface conditions, porous fomite, non-porous fomite, any of these other confounding factors that we're not taking into account when we just say one cell per hour is going to die off. We need to understand realistically what is the survival of these organisms. And then this one is Microcystis aeruginosa. It's the blue-green algae that shut down Toledo. It is a microorganism. It doesn't particularly pose any kind of pathogenic hazard to us, although there's some questioning about that now. It's a toxin now that we're worried about. However, it's a microbially derived toxin, very similar to what a lot of cases kills some people with other pathogens or significantly harms them. But it's still microbial, so we need to be able to figure out, we can't just keep punting it to the chemical risk assessors. All right, that's your job now. They have enough that they need to worry about. This is going to be our field. We need to handle it. So we have a little bit of an idea on where we're going, where we come from and where we're going in QMRA. Now we're going to go through a couple case studies to kind of weave our way into indoor space contamination that's directly applicable to healthcare settings. Really hard to see, but what we're going to talk about right now is drinking water infrastructure. And one of the reasons that I start with drinking water is if you're talking about a wide-scale impact for a population health, as on the order of the entirety of a city, drinking water is a darn good way of being able to approach that. All we have to do is look at incidents like the Flint water crisis, where entire populations end up getting impacted because of one dumb decision. And I'm going to say it's a dumb decision because you need to prove a public health benefit before you change your source water. It's written in the regulations. Nobody did that. Nobody checked to see if anybody did that. So it was one bad decision that actually caused the problem. Anyway, so if you want to affect an entire population, drinking water is a very good way of doing that because the entire population is consistently exposed to it. Even if they're not drinking out of the tap, every time you flush a toilet, you get this beautiful plume of aerosols. That to me, it's beautiful because it's nice to model. But you get this plume of aerosols that gets shot up, and you're either going to be ingesting that because it deposits in on your mouth when you breathe in, or you're going to inhale it as well. And that's just one thing. Talking about showers, taps, leaks within the building itself. There's a lot of different ways of being exposed to tap water when you never intended to even use it. So even if you're only bottled water ever, which is still a bad idea, you're still going to be exposed anyway. And the other thing about water is I put everything as the idea of the survival of threes. And it's just a general rule of thumb. I smoked for 20 years. I'm not going to go 3 minutes without air. I'll probably go a minute and a half without air, and that'll be about it. But when we look at it is we have water as a significant need in an overall sense. And I usually put up a quote from William Clark about being able to impact public health in a very grand way through water in general. But the other thing that we need to understand is, in reality, where we have to be able to build these models from. So, what is the purpose of cake? There is only one purpose for cake. The only purpose is to deliver frosting into your mouth. So the cake is the basis for all the other stuff that you actually do want to eat. Models are basically the same thing. We need to start from somewhere. So we start with the cake model, the basic model. It's rife with assumptions. It stinks. It probably isn't going to work overtly well, but it gets us somewhere. It gets us started. And then we can start evolving it from there. One of the issues within the HAI world is that a lot of the cakes have not been baked yet with regards to the modeling. So we have some agent-based models, we have some infectious disease transmission models that have been built out. But we're talking about a significant number of domains that need to be coupled together into one overall analysis, and both of those can either couple those or be scalable. They can't typically be both. So you need something that's scalable and can couple multiple domains in a straightforward practice, and QMRA is a way of being able to get to that. But still within the drinking water system itself, this kind of goes to the overall behavioral aspect of it, as well as how that ends up impacting our overall exposures. So we like to advertise water, and I'm a water engineer. We like to advertise water in a couple different ways. So this is Fairmount Water Works, first filtration plant in Philadelphia. And there's the art museum in the background, and it's a nice, pristine-looking river, even though that's the Schuylkill River. And if you go and swim in that, good luck. You'll probably run into something you don't ever want to touch. So that's how we like to view it, and then we show the new infrastructure getting put in place. It's all nice and clean, and it's going to be protecting the health. And then the education into the future generations of water engineers, who this is Charles Weir, and any donations to his college fund is always gratefully acknowledged. But we have the educational impacts that we can look forward to with STEM outreach in the drinking water world. And then we have the reality of drinking water infrastructure. Not everything is this bad, but there's some bad stuff. I am obsessed with wood pipes because holy cow, we still use wood pipes. Isn't that amazing? Just in 2007, Philadelphia had a wooden water main break that they didn't know was still wooden. So this is a wood water main. And it is slats of wood that have a coating on the inside to keep it watertight, and then it's bound together with metal straps. We have a bell end of a cast iron pipe sunk into a wooden pipe because, well, we can't dig up the entire street to get all of this wood out, and we don't know where it ends, so let's just put the cast iron in it and then hope for the best. That's not the entire idea behind it, but there it is. And again, my obsession with wooden pipe is there. This is actually a set of biofilms that built up varying layers of calcium buildup. There's more to it than that, but it's a really good depiction of what actually ends up happening on the inside of pipes. So this was actually a wastewater pipe, but I use it because it's dramatic. and it looks less gross. The drinking water biofilms are sticky and kind of mucousy looking. But you can see that we started with a very large pipe. This is actually a 2.5-foot sewer main, what it was originally supposed to be. And then calcification just started eating that all away. And microorganisms were driving a lot of that in this case overall. So we have a dichotomy between what we like to think of by way of drinking water infrastructure and what we actually see with drinking water infrastructure. And so there's a lot of problems. And one of the ways of being able to address a really complex situation without a lot of data is via simulation. And so getting the data is expensive, time-consuming. The people doing the sampling don't always understand the idea of a power analysis for representative sampling. And so there's going to be a gap between the data that you want, the data that you need, and the data that you get. So in between that, we can use simulation. And QMRA is very useful and very good at building out simulations to target what data to get, in what way, in what numbers. So that's one other benefit of QMRA. You can make decision analytics models, and then you can target future science using it. All this plot is showing you is simulating the mean of a standard normal distribution, 0. We're just simulating 0. There's only one reason to do that, and that's because you want to have a pretty plot like this. The whole point is a simulation leverages the law of large numbers. That tells me that after I've taken enough samples, my sample mean starts to approach my population mean. So no matter where I start from, I'm going to end up simulating 0 at some point. Stretch this out farther, and I'm going to get tighter and tighter along this red line, which is 0. It's never going to actually be 0. It'll cross over 0, but it's always going to be bouncing because it's a simulation. We're not actually saying 0. We're simulating 0. So we're going to do the same thing. We're simulating a health risk, but we're not actually going to say, this hospital has a 1 in a million risk. So one person out of 1 million people that come through this hospital will get sick. We don't say that because we can't say that. There's an estimate that the probability is, because that's about as good as we're going to be able to get. We cannot perform magic. The smart systems analytics and the smart systems algorithms, they are not magic. This is not my magic wand. They are just our best approach to be able to simulate what's actually happening in the physical world. So now what we want to do is we want to look at a case study within Legionella pneumophila. So Legionella pneumophila is a really interesting one, interesting pathogen in general, but one of the more interesting pieces of it is either it's because we're looking for it more, we're reporting it more often, or the overall growth is actually increasing, but it has overtaken all other waterborne agents in drinking water for disease impacts. So, I mean, it has either accelerated in its impact in us, its pathogenesis, maybe it's changed, it's more virulent than it was before, maybe we're looking for it more often, or maybe we've killed off all of its competitors in the drinking water biofilms, and so now it's going to be able to grow at a higher rate. We don't know. One of those things could be possibly happening, and we hope that it's probably not the growth in biofilms. However, if it is, we can try and simulate our way through this. So if we want to be able to get a good prediction of what the concentration of Legionella is in a biofilm, but we can't actually sample that biofilm, what we can do is we can run a simulation to try and make our way through this overall. So we need to be able to account for nutrients coming in. We need to account for stressors coming in, such as chlorine, monochloramines, things like that. Monochloramines are a little bit better at getting into biofilms, but they're still not doing a very good job on Legionella in a biofilm anyway. But we need to account for all of these factors and processes within whatever the model is. And in this case, particularly for Legionella, all of the experiments are done in univariate space. All of them. Somebody looked at organic carbon and how that affects growth. Somebody looked at iron and looked at how that grows. Somebody looked at monochloramine or chlorine or something else and saw how that affected decay of the organism. They didn't do it in multivariate space. They didn't look at a combination of a nutrient and a stressor. And if they did, they have 2 data points. What can I, as a modeler, do with 2 data points? The answer is bupkis. There's nothing you can do with 2 data points other than draw a straight line through something, and that's not very valuable at all. So the data that is out there, it limits us in what we can do, so we can only do a multiple linear regression. I don't like multiple linear regressions. They're empirical models. I like mechanistic models because they're going to be more accurate, scalable, and movable. However, simulation can give us a way out of this. We have empirical constraints due to the model we have, But then we run it through a two-dimensional simulation to try and strip away some of those empirical constraints. We're not going to eliminate the empirical constraints. We're just going to remove some of them by simulating over 1 million iterations what's happening in the biofilm with regards to growth of Legionella in the system. I don't have a ton of time to linger on this, but you'll have these slides and you can kind of look through the algorithm that we have. Algorithms are math, but they all start with these kind of flowcharts. You need to be able to have decision points of where the program is going to go, and the flowchart kind of makes your life a lot easier if you do it that way. But what we want is we want to be able to have some kind of descriptive model, then simulate our way through to try and remove some of those empirical constraints. And if very, very quick primer on two-dimensional simulations, you sample something that you consider variable, you take that value and you process it through values that you consider uncertain, and then you end up you just keep doing that over and over again. So in this case, what we said was we have a variable temperature and variable time, and then we have an uncertain iron concentration. Organic carbon couldn't even be put into this because the data was so bad. And so after we run through the two-dimensional simulation, what we have is we have a not overtly good estimate of what a growth of Legionella could be in a biofilm given specific conditions within a water utility. This model should never be used. How many times have you heard a modeler say that, right? This model should never be used. The purpose of it is to show by having limited data, we're limiting our ability to have some kind of predictive estimate of what the concentration of a significant health hazard can be or is. And that's because we're not running the experiments properly from a modeling context. So if you're running experiments, or if you know a friend or a colleague who's running experiments, please have them talk to a modeler. If it's not me, any other modeler. And we can help them figure out what kind of data is necessary at what levels in order to use the data in a broader sense. So this one we're going to go through is an example of how QM can be used in order to affect design change. So in this case, the design change ended up being that the spray park closed because they just didn't want to spend any money on it. But what ended up happening was this. It started out with an outbreak of cryptosporidiosis at a recreational spray park in upstate New York. Now, if you don't know what a recreational spray park is, it's basically kids that you're afraid are going to have trouble swimming, or you don't want them to swim. They'll play in a spray park and they'll spray water on them, and then they have fun and stuff like that. However, kids being kids, almost always, there's one kid that bends over one of the spouts and then shoots the water into another friend's face. So you can kind of picture what's actually kind of getting shot into that poor kid's face. So, however, what ended up happening in this case was we had an outbreak of cryptosporidiosis. It was confirmed as cryptosporidium through lab sampling within the cases themselves. So we had two objectives that we really wanted to address. First one was, what was the likely dose that the children were exposed to be able to say what happened. And to be able to say what happened is, did the system break down? Was it just an inordinately large event? Children have accidents. So what actually happened is to be able to try and backtrack what happened by way of calculating what the dose was. So what we did in this case was we first built out a cohort trial or cohort study and broke them out in exposed, unexposed by way of the cases that we had. And we back calculated out a dose. That wasn't as interesting as the second objective. And the second objective was to develop a risk model to be able to analyze what future design changes to their reclamation system can be used. So any pool typically will take water as it flows through, goes through some kind of filter, then gets chlorinated, then gets put back out to the pool. It's not continuously fed with tap water, which probably everyone knows this. So they have some kind of water recycle system. It's not really any different from water reuse systems. It's just, it's not intended to be drinking water. It's pool water. So what we did was we have where they're recreating. The original design had it come into a certain central tank, then go through treatment, and the treatment was a multimedia filter and chlorine. If you know anything about cryptosporidium, you know that that's probably going to do almost nothing, but they had a fairly good slime layer or a Schmutzdecke at the top of the filter. I love saying Schmutzdecke. At the top of the filter, so we gave them some log credits for that. But the chlorine, they had absolutely no log credits because chlorine doesn't do anything to crypto unless it's in such high levels, you don't want to touch that water. So once it goes through that, it gets reacting in a tank 2 with the chlorine, comes back to tank 1, and then goes back to the spray pad. So the engineer in me saw this arrow here and said, huh, that's dumb, because what we're doing is we're mixing clean water and dirty water. And you can kind of do that sometimes. If you have a big tank and the dirty water comes in at the bottom, which is usually a little bit more dense because it's got solids and things like that, and then you have the clean water come at the top, and then the outlet is at the top as well. You can kind of get away with it. We don't do it anymore because we became smarter. But in this case, what they did was the inlet and the outlets were basically all on the same level. It was a small tank. There wasn't really anything that was causing raw water that was not treated being just sent back out to the spray pad. So at first we called this the dumb pipe, but then we decided that's too harsh. We'll call it the bypass pipe, because all it's doing is it's actually allowing for the bypass of the treatment overall. And so basically we have two bypass pipes, one that comes from tank 1 back to the spray pad and one that goes from tank 2 to tank 1. Whoever designed this, and nobody signed off on it, which was an interesting thing to find out, is an idiot. Before you start any risk analysis or any computational effort, you need to answer a couple key questions. In a lot of cases, I usually have like a basic journalism slide on this: who, what, when, why, and where. Who's the population exposed? What are they exposed to? How long are they exposed to it? Why do I care about this? Other than you're paying me to do it, so I care about it. But what we needed to understand was there has to be some way of being able to compare risk from one design option to another to be able to show not only is it just stupid to have that pipe there, but the system isn't built in order to work with cryptosporidium. Your population has been exposed to cryptosporidium somewhere else. This is why they're shedding it on your spray pad. You might have another incident again. You might want to do something by way of trying to treat for crypto. So what we did was we went through Markov chain modeling, and this is a very, very brief primer on Markov chain modeling. We used a discrete time Markov chain, and what a Markov chain is doing is it's saying that there's physical states that something or someone can be in. I can be in state A, which means I'm here talking on the microphone, or I can be randomly decide to go over to state B and sit down because I got bad knees and I just don't want to listen to my own voice anymore. So there's some random probability that that's going to happen, and we can model that. Now, that's not overtly useful. That's just a binomial event. I'm either here or I'm over there. But if we take that same concept and we include, those equations look terrible, but we'll have to address that in a moment. So the value of it is, instead of just saying it's a binomial event, we put in physics, biochemistry, and microbiology into this one parameter. So this parameter, this loss rate of lambda I, becomes a set of equations or an equation that describes a physical or a biochemical or a microbiological process that affects the survival of an organism or the transport of an organism or the ingestion of an organism or something else. How is that organism changing states? We can put in the mechanistic aspects of how it changes states within our parameters here. So we have a probability that you're in one state and you stay in that state. So my probability of being here and staying here is very high for the next 9 minutes and 38 seconds. Ooh. But what we can also do is we can say, what we want to do is we want to say there's a probability that I'm going to be here and I'm going to move over to there, and I'm going to take all of the processes that would keep me in this state and use that in the denominator, and then divide the processes that would take me from one state and move me to another state in order to be able to predict or give a probability of moving from one state to another. And then we then weight it based on the probability that I'm going to stay here. When we're talking about doing a Markov chain, we're talking about doing it within microsecond timescales. So within 1 microsecond, the probability that a pathogen suspended in the air suddenly decides to really quickly settle down to a surface is fairly small. So the probability that it's here and it stays here should typically be the higher probability, and that's what we're doing in those equations. So now that you understand a little bit about Markov modeling, these flowcharts now make more sense with all these lambdas all over the place. So we have The original configuration, we have another configuration where all we did was remove the bypass pipe and then put in a proper return from the second tank. Then what we had was we put in an ozone contactor and removed the bypass pipe, and I forgot to delete that arrow. Sorry. So that arrow, there's nothing happening there. There's no arrow there. So we put in an ozone contactor. We also did a couple other ones where we had UV instead of ozone, and we decided to go super overkill, and we had ozone, then UV, then chlorination, then send it back out. Because if you're simulating these things, you might as well go super duper overkill on things. So these are the loss rates as we go through, but we don't have enough time to really explain these. I can describe these more to you if you're more interested in them. But basically, we need to take into account advection through the system itself, so the bulk fluid flow through the system itself, and then what could be possibly removing the pathogens. They either die on their own, get trapped in the filter and die, or they die due to chlorination or the ozone. So in order to actually model the risk, what we needed to do is put that into a dose response. So the Markov chains got us a concentration coming out from the spray pad. So what we said was a child had an average incident on the spray pad. Nobody caught it in time. It all washed down into the reclamation system. And now what we do is we go through the treatment and simulate out what the concentration was to the spray pad. And that's the dose after you put in an ingestion rate. But you get the dose from that concentration from those Markov chains. So this is just the exponential dose response model. And what this is saying is that there's a dose that the host is being exposed to. And then R is just the probability, R is just the probability that that organism or set of organisms are going to survive to get to an infectious point and cause an infection. That's all that really is saying. And there's some probability of infection based on that. But in this case, because we were in an outbreak scenario, we needed to understand illness. So we take our dose response model and multiply it by our morbidity ratio, and that gets us a probability of illness from our probability of infection. There's a couple different ways of doing that to be able to get to a probability of illness once you have a probability of infection. But one of the more straightforward ways is to understand the morbidity ratio. And in this case, this comes from the EPA, and it's about 50%. So 50% of infections go to illness for crypto. Average. We talked about drinking water infrastructure, then we talked about Legionella, then we talked about Cryptosporidium, but they were all in water. But now how do we get ourselves back into indoor spaces and hospital settings? And I forgot about this slide. Apologies. These are the results of the model overall. What we're showing here is this is if you don't do anything to the system. So this is the original configuration. This is essentially somewhere between 0.95 and 100% risk. Never, ever, ever do we want to see this bar. But in this case, because we have a bypass pipe and we have treatment that's not really doing anything for crypto, that's what we're seeing. And then this is illness, which is just half of what the infection is. If we just remove the bypass pipe, and it might be a little hard to see those numbers, it's hard for me to see those numbers, we basically get a 10% reduction in our highest risk. So instead of seeing our risk being almost 100%, 60% of the time, we see it at almost 100%, 50% of the time, because we removed a bypass pipe from a treatment system that isn't designed for crypto. And then if we expand this out a little bit more, when we look at ozonation or UV, we see these high risk levels dropping more and more and more. And you're never going to get to a very low risk. You're still going to have some high risk because crypto is hard to kill, and we put it as though somebody pooped directly on the spray pad and it washed down into the system before anybody caught it. Apologies for that. Now what we're going to do is talk about indoor spaces. First thing that I want to do is I want to go to this real quick. And this actually just recently came out, but it's an interesting link between what Dr. Reynolds and Dr. Gerber were talking about with surface contamination and HAIs. And one of the predominant HAIs is central line tube infections. And this was a partnership with somebody who works at Toyota and a set of children's hospitals. And what ended up happening, the link will be there on the updated PowerPoint because this just came out yesterday. What ended up happening was they found that even though the nurses and the doctors had cleaned their hands and sterilized the tube, every so often when they're donning protective sterile gloves, they'll put the tube down on the bed or they'll put the tube down on a counter surface that is assumed to have been cleaned and disinfected, but it wasn't. that's what was actually contaminating the tube, pop the tube in, and now you have a risk of central line tube infections. So it was interesting that it wasn't a glorious academic like myself who discovered this. It was a partnership between a person who works at Toyota and a set of children's hospitals. But it was a way of showing that surface contamination has a serious effect on HAIs, especially something that we may not have thought of before. The tubes are in sterile packaging. They're sterilized. They're put in sterile packaging. You put on gloves. You open up the sterile packaging. But if you do a little bit of that wrong, you've opened it up, then you put on the gloves. In order to put the gloves on, you put the thing down on a bed or a counter or something along those lines. Adherence to protocol is never 100%. First law of thermodynamics, you cannot have a system that is 100% efficient. You can never get somebody to hold to a protocol 100% of the time. So assuming that is going to be something that's dangerous. So if we go back to the slides. All right. So that was an interesting piece that just came out yesterday, and not in the journal, but ToyotaDriverSeat.com. I'm a Subaru driver, so that's not a pitch for Toyota or anything. The point of it is that the surfaces that we're talking about are fomites, and you heard a bit about those yesterday. And what we're looking at in this case, this particular model, is we're looking at a shared office environment, a simulated shared office environment. So we have somebody using a mouse. The mouse is a plastic fomite. There's a certain risk of contaminating your hand with a pathogen from touching the mouse. There's a plastic fomite on the computer monitor. There's a wood laminate fomite. And these all have different transfer efficiencies and transfer rates. We need to be able to understand that in an indoor space, if we're just talking about fomites now, there's the desk, the handle, the door, the spout on the coffee. If you decide to do some push-ups for whatever reason, the floor, the chairs, your book, your computer, whatever it is, you have to be able to account for all of them because they all might be contaminated with something. So even if the contamination is 0 or very, 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 very low, you still need to account for it. And mathematically, we do that through the inclusion-exclusion principle. Basically, think of a union, and all we want to do is we want to account for absolutely everything and how that turns into the coupled risk that we're interested in. So 2 things to understand when we're talking about a fomite QM array. One is that recovery from fomites is not a straightforward process. If you choose too small or too large of a surface area, your data is not going to be very representative. What we want is data that's representative of the population of contamination, and we then want to be able to take that and use that for data that's representative for the contamination of a population in that room. So basically what we're seeing on these plots is within these 6 fomites, sampling about, 100? Yeah. Sampling about somewhere between 5 and 10 square centimeters is going to give you the best overall recovery for these specific surrogates that we're looking at. Now, using that, we go into a much more complicated Markov model. And this is complicated because we have one person who's going to contaminate multiple fomites. These fomites are contaminated. They're going to result in total number of organisms that the next person in the room is going to be able to be exposed to. They're going to contaminate, they're going to be on these fomites. Those fomites are going to contaminate the person. The person in turn is going to recontaminate the fomites again and ingest or contact a mucous membrane or something along those lines to be able to get the pathogens into their body for a health effect. And then we go on to the next person in the room, and we can keep this going until all of the organisms are dead or somebody else comes into the room. One thing I always tell my classes is kind of 2 things. Nature is inherently lazy. That's why you go from high concentration to low concentration, and humans are inherently gross. We contaminate everything almost all the time, even when we don't intend to. So we're not going to belabor on those Markov chains because I'm already over time. But what we can do is we can go back to this inclusion-exclusion principle, and we can either merge all of those concentrations together and say, this is the target concentration we want to be able to reduce so we can target these fomites, or we can be more useful with it and we can build out a risk model. And the risk model will be able to tell us which one of the fomites presents the highest level of risk to the population in that room. This was a shared office environment. And so we basically allowed it that every single fomite had an equal probability of being touched or an equal rate of being touched, which is not accurate. This is the cake. But it's a fancy enough cake that we can publish it and talk about it. So what we can see is that once we combine all the risks together, we get a picture of what the actual underlying risk for that population is. And then we can look back and say the aluminum is going to be our highest risk point, probably because the transfer efficiency from aluminum is a lot higher than plastic or wood laminate in this one. And then we can put in porous fomites, bed sheets, pillows, put in non-porous fomites, counter surfaces, desk surfaces, all these other aspects, and be able to get an idea of what the actual true underlying risk of HAIs is based on simulating the real world. So where we want to try and move forward, and I won't talk too much about this because like I said, I'm over time already, but where we need to go a bit into the future is not only do we need to understand there's multiple pathogens people are exposed to, multiple pathogens and multiple chemicals people are exposed to, and all of that results in a health burden. Not a disease burden, a health burden. So where QMRA can go into the future is not only answering mitigation options and decision points within HAIs, but it can also start incorporating all these other stressors at the same time and move beyond QMRA into a more evolved quantitative risk assessment that we can go to. So that's my little soapbox at the end, and now I'll stop talking.
Thank you very much, Dr. Weir. We have some time for a few questions, but beware, he's an honest man, so he's going to give you an honest answer to your questions. So,
great presentation, Mark. Thank you very much. Two things I wonder if they are being addressed in QMRA or if they can be in the future. And so just looking at the temporal changes in the physical environment in a hospital and how that can be impacted. And I appreciate that you've got the lambda loss rate in your Markov chain model. But I'm looking at activity and practice. So for example, if an equipment room is accessed 100 times in a 24-hour period and there's a nexus there, or if you've got a bathroom that's disinfected once a day, somebody's shedding C. diff into it 10 times a day, but staff are entering it 20 times a day. Mm-hmm. And you know how that can go into your model. So that was, I guess, question number one.
If you think back to the flow diagrams for the Markov chains for the indoor space
Yes.
area, some of those lambdas did have temporal components. So we had the frequency of touching, we had how long the person was in the room, then we had a hold time. So there was a hold time between one person in the room to the next person in the room, and that allowed for decay of the organisms to an extent.
And does that also allow for growth? So for example, over a 24-hour period, so if you've shed at 9 a.m. in the morning, but it's not going to be disinfected until 8 a.m. the following morning.
Yep.
Sorry.
Yep, basically we can do that. So what we're seeing is once we get to this point, this is actually a little hold period before we get to that point. And so if you're talking about it from the crypto spray park example, what we have is we had just one event. What you could actually then do is you could have multiple events. So it's not usual that a massive load of diarrhea comes out while you're recreating, right? It's usually little dribbles that start coming out and then you don't notice them. So we can do, so that's basically the example between a point source and a continuous source of contamination. So we can do either one of those. We can have it where there's a growth happening. So that goes back to the persistence. If we just look at decay, we're only looking at the death. If we look at persistence, there's an opportunity for growth. So we have it decaying down, then it shelves, and then it decays more. But then there are growth curves or persistence curves where we can have it come down, shelf, come up a bit, and then die off again.
Fantastic.
So we can have a lot of different ways of doing that. And that's what I say, merging these domains. And so that domain is a temporal spatial scale as well as a behavioral scale. How often was it disinfected? Was it disinfected properly? Those kind of questions can easily be incorporated into a QMRA. And those are really big questions.
Right.
Yeah.
Wonderful. And then the second one is more on the response side or the susceptibility side. And specifically looking at things like relative humidity within a hospital environment. So patients are getting dehydrated, they're more susceptible to picking up viral transmission. And it's also actually on the spreadability side where you've got greater viral shedding and greater viral transmission distance and time in the air as well with lower humidity. Mm-hmm. And have you got a way to model that in QMRA, whether you got 20% relative humidity during flu season versus 50%, for example?
So that would be, so there are two ways that that can be addressed. One can be addressed in the exposure side. How is the exposure being affected by way of the humidity? So are they aggregating due to the humidity? Are they settling at a faster rate or a slower rate? Are they more suspended for a longer period of time than being exhausted from the room, which makes it a little safer for everyone in the room? So there's the exposure side of things, and that's only a couple items. On the other side of things, we have the human susceptibility question. Is there an increased susceptibility? Now, where QMRA really ends up shining on this is the exposure side. That's dead easy. We can do that if we have the data. If we don't have the data, we know the mechanisms on viral aggregation, so we can model that. That's going to be easy. The more difficult one is including that susceptibility aspect. And that's something I didn't get to, which is one of the pieces of QMRA that needs to happen in the future is a much better merger with epidemiology. It's not the same as just saying this is my case burden and this is my risk estimate and where do they converge. It's a matter of being able to understand increased or decreased susceptibility over time under different environmental conditions and so forth. And so part of that is my PhD student's thesis looking at modeling the pathogenesis of Legionella. So if you can model the pathogenesis of Legionella from biofilm to lung, then you can get an understanding of, and that's basically going to be a really fancy cake model. You have an understanding of what's happening in a macro level, then you can refine it at a micro level to include other additional factors like relative humidity, time, and temperature at the same time. Well, time's going to be in there, but temperature as well. Room temperature, not water temperature.
So say, for instance, you do an assessment of a building to understand your risk for Legionella pneumophila, right? So you have an understanding of the building and the population that's within that building. When you get done the QMRA, how translatable is that to another organism, say Pseudomonas aeruginosa? If you did the assessment with pneumophila in mind, how could you also relate that to another system-wide or potentially system-wide organism like Pseudomonas aeruginosa?
So that's a really good question.
Thank you.
And your question was very good as well. I don't want to be playing favorites. I should be a senator. But especially your example on Pseudomonas aeruginosa is that causes a pneumonia as well that we're predominantly concerned about in indoor spaces, right? It has a similar pathogenesis, so we're going to be able to model it in a similar way by way of the overall exposure from air to lung. So that's going to make it easier to go from Legionella to Pseudomonas. However, Pseudomonas can also cause bacteremia. It can also cause ocular infections. So those are two different exposure pathways that need to be addressed. The not so simple answer is if your exposure pathway changes, then you need to develop out not even so much a new QMRA, but it is a new QMRA. So you don't have to tear it down and start from scratch. It's basically my exposure pathway isn't working anymore, so I'm going to gut that, and the dose response is going to change, and a couple other things are going to change, but the basic guts of the model can stay the same. So it basically takes your development time and turns it into half or three-quarters of what it originally was.